We're good.
Okay, so the last talk of the session and the last talk of the entire workshop. Quite an honorable place to be. Shea Hess Webber from Stanford is going to talk now about FarSide imaging. All right, take it away and I'll give you the 3-minute warning. Are you speaking? We see your slides.
Unmute. Sorry about that.
Okay.
Once I share, I can't see myself anymore. So, yeah. So it's a little bit interesting to be in the space weather session talking about helioseismology, but I think it's also really exciting. And we've sort of hit on earlier today, Cooper and a few other people talking about how, you know, the boundary conditions at the surface are really important in terms of modeling and, you know, extending outwards, if you will, downwind for space weather prediction and modeling. So our goal with the work that I'm going to be presenting here is to sort of aid in that effort. Let me see. Here we go. So there's a lot that I'm going to be talking about, so I'm going to kind of breeze through a bunch of things, skip over a couple details, but hopefully we can have a further conversation, at least in chat or in the breakout rooms. But so here's sort of everything that I'm going to try to push through. So to start, background and motivations, this is really the connection to space weather. As we all know, the sun or space weather is driven by the sun's magnetism. Right now, when we talk about, you know, magnetograms of the sun, they are synoptic maps, which means that it's not any one point in time. It's taking only the central meridian and kind of unwrapping the sun as time goes by. And that's not really what we want for accurate modeling of the corona and you know, interplanetary you know, space weather. So what can we do about that when we don't have a view of the far side of the sun? So we've had in the past observations, direct observations with stereo, but they were not magnetic observations. And at this point, the stereo, well, we don't have stereo B anymore, and stereo A has rotated it back around towards the far, or towards the near side. We've had acoustic maps in the past, but again, those are wave phases and not magnetic field measurements directly. And so what can we do to try to use what we have already? So the far side instrument or observations that we have, and the near side acoustics, or the near side Doppler field, to be able to look on the far side, but relate that to the magnetic field. And we've just sort of, you know, I think that this point has kind of already been driven in by some of the talks that we've seen already today. But if we look at this map of the far side and looking at different active regions, you can see in terms of how close you are and how far you are from the sun in terms of the Q maps and the coronal holes, this currently synoptic map makes a big difference for what you actually see coronally in the coronal models. So we really need the global field to be able to get an accurate picture of that. Just in terms of, you know, how can the far side really make a difference? We took one of like a snapshot of Mark DeRosa's flux transport model and embedded a pseudo emergent far side active region and looked at the Q maps of, you know, how that affects the structure of the magnetic field at R 2.5 of the sun. So this is actually an active region that we knew was there after it rotated back around to the near side. So we can actually compare the results of the Q maps to coronal observations here. So on the left, I don't know if everyone can see my pointer, but on the left side, you can see the results of the models without the artificially embedded active region. On the right, you can see that we've included the artificially embedded active region. And then we zoom into sort of the central strip of the Q maps and compare them side by side with actual coronal observations. And you can see that with the FarSide active region embedded into the flux transport model, the structure of the corona at 2.5 solar radii is much closer to what we actually see in the LASCO C2 observations. So I'm just going to keep moving on here. Our ultimate goal for this project is to come up with a reliable, as near real time as possible, FarSide magnetic flux maps that we can use to assimilate into various space weather models that is solely dependent on near side observations. So we don't need to have, or not that we don't need to, we would still like to have the FarSide observations, but that we can use at least as a first step to get synchronic global field maps at the surface, global flux maps at the surface. So jumping into the FarSide acoustic maps, we have published, Jinwei and a few more of us have published a new FarSide acoustic map methodology that gives us more spectral resolution. So I'm not going to get into a whole lot of details here. Suffice it to say that we have we're using more skips around the sun, so we can we have more data for any given point on the far side surface, which allows us to use less time to integrate. Instead of, I think the Charles Lindsay's methodology used 4 prior days of integration of the acoustic maps in order to get a picture of the far side active regions. And we are using 3 days prior. So it takes less time integration for us to get a similar picture of the far side. And I'll talk a little bit about those statistics. So here's a little bit more information. We can get very close to the limb. We can actually see further, like around to the near side than the limb, but we tend to cut off at 180 degrees and use AIA or HMI data to look at the near side when we're creating our synchronic maps. We have data currently from the beginning of the SDO mission through today and counting, and we are actively working on getting this data. So the pipeline code is ready. We're getting ready to ingest everything into JSOC, and the acoustic maps for the far side will be available shortly. And we have a recent paper. Actually, I don't know if I included the reference to that, but a paper that came out at the end of 2019, I believe, Jinwei can correct me on that, that goes into further detail about the helioseismic process that we're using. So this is just a comparison between the previous FarSide acoustic maps and what we have now. We don't want to downplay the previous maps. The holography maps have been really useful and important for space weather and will continue to be important. But we just wanted to highlight sort of the differences between those and the new method that we're using. We also wanted to show a comparison of Charlie's maps, which are at the top and with the yellow, and our maps, which are at the bottom in orangey red. And so we're going to be highlighting a couple key regions here to look at. So first side is we want to make sure that we're capturing near side active regions that rotate around to the far side. And you can see in the middle here, we're not capturing everything immediately as it rotates around, but we are capturing, at least in this instance, we are able to capture some of these active regions as they rotate around before the holography maps are able to. And then we also do a good job of, once they've rotated around to the far side, of capturing them as well. In terms of known far side active regions returning to the near side, you can see as we approach the limb of the sun, we're still able to detect these above the noise. You maybe can convince yourself here that the holography maps can still kind of see these active regions, but they're more within the noise at the limb. But so we can actually track these fairly well back onto the near side. But most importantly is we want to be able to detect new far side emergence. And so this in blue is an example of a new flux emergence, a new active region emerging on the far side that we have detected before it's showing up in the holography maps. So this is, again, just another example. You can see on the near side, we have the HMI line of sight magnetic field on the top left, STEREO AIA on the bottom left, STEREO EUV merging both the A and B on the bottom right, and then using the helioseismic acoustic image for the same time, you can see that we're capturing these active regions for this date and time, the synchronic picture all at once.
You've got about 3 minutes left.
Oh, okay, I need to hurry up. So we can talk about the statistics of this during the breakout session. I'm going to keep on moving. This is just essentially to say that we're doing a lot of pre-processing and setting up of our training for with using near side data, HMI to AIA, magnetic flux to 304 angstroms. And this shows sort of how we're dividing up the data in order to do that machine learning. We're using a UNet. Raju can talk about this a little more if people have questions on it in the breakout session. But this is a way to basically train taking images of 304 and converting it into line of sight magnetic field. So this is all using near side AIA to HMI data, but then we can then take this algorithm, this training, and apply it to the far side. So here's the results of the near side. And you can see it looks pretty good, the comparison between our AI generated and the HMI line of sight. You can see the statistics here. It's a pretty good linear relation. So the flux levels are well calibrated. And then we can apply that with some pre-processing. Again, gonna skip over this in want of time. But you can see that when we apply things to the far side EUV data, and then compare the intensities synchronically, you can see that they match up very nicely. And then this looks like a very similar plot, but this is actually the total magnetic flux comparison. So this is EUV comparison and the magnetic flux comparison, and we're doing a really good job of capturing that using this near side trained algorithm on the far side stereo images to get far side magnetic flux. But we only have a certain amount of time for the stereo data through about 2014. So we need some way to be able to extend this into beyond 2014 and into the future from here as well. Again, I'm going to skip this for want of time. It's another example of how we're doing well matching the magnetic flux. So looking at the acoustic maps, or trying to transition acoustic maps into magnetic flux, we're again using a very similar algorithm, a UNet structure. And sort of just to compare the data set that we have to work with, we have a lot less data here. And the spatial resolution is a lot lower because of the acoustic maps having just inherently low resolution. So we don't really have enough for a validation set, but so we can't really dig into that, but there are other ways that we can do some statistical analysis. Again, we're gonna have to talk about that in the breakout sessions if people are interested. But so here's the results of this secondary machine learning. We're taking the acoustic maps, an example on the left here, the EUV-derived magnetic flux that we used with the near side training on the top right, and combining those with this new machine learning algorithm to get the far side magnetic flux that is solely dependent on the near side Dopplergrams. So you can take a Dopplergram, create an acoustic map, and get this far side magnetic flux map out of it. We're doing fairly well in terms of our correlation coefficients and the machine learning, what the machine learning is spitting out. It's very promising. We're still tweaking some things a little bit. Since I first created these plots, I know that some of the data preparation in terms of normalization, like instrumentation normalization between the stereo observations of A and B and with AIA have improved. So we're still working on improving this result, but it's looking really good. And I believe that for the machine learning algorithm that we have currently, we've run most of the data through, I think maybe the end of last year. You can correct me on that. But so here's our 3 different data sets that we have. I would like to say check tentatively that we've reached our goal. We've created this near real time far side magnetic flux map that's based only on our near side observations. Again, there's not a lot of time to talk about this, but we made a comparison between our far side magnetic flux maps, synchronic maps, to a couple different surface flux transport models. And I just want to shout out to Lisa. She and I are going to be co-mentoring a REU student this summer that's going to try to take our far side magnetic flux maps and assimilate them into her advective surface flux transport model. And so stay tuned for the results of that. It's going to be pretty exciting. We've definitely got ongoing work. We're creating a website where you can access, at least for now, the acoustic data and eventually the far side magnetic flux maps that are acoustically derived. We're ingesting the acoustic maps into the JSOC. And again, I believe that we have the magnetic flux maps as well, but they also aren't quite in JSOC yet. So if you're interested in playing with them, reach out to us and we can get you some data to work with. And yeah, that's it.
All right, thank you. And I think we've run significantly over time, so we'll take, I know Craig before us had a quick question, but let's take that to the breakout. So